All right, let's talk about global warming. Most people lump it into a single thing, and whether we should believe it or not. But really, there's several different questions in here scientifically that we can break out and talk about separately. The first question is the Earth currently in a warming trend? The second one is this warming abnormal? One of the recent arguments has been, well, sure, the Earth is warming, but it goes up and down all the time, and this is just normal warming. So is there a way to know whether we're just part of a normal up and down cycle? What do we know about global temperature? What factors affect it? Atmospheric gases? And lastly, are humans actually causing warming? And a more subjective question, which is often rolled into there, is warming a bad thing? So we'll talk about that too. Because remember, from a scientific point of view, if we have a very subjective question like, is it good or bad, we need to change it into something that we can answer scientifically. So first, is the Earth currently warming? Well, here's just since 1880. Here's a temperature trend from 4 different sources, from NASA and NOAA, the National Oceanic and Atmospheric Administration, Japanese Meteorological Society, Hadley Center for Climate Research, and they pretty much all agree that, yep, in the last 150 years, things have been pretty much steadily warming. Is this warming unusual? So now we have a temperature record here going back 12,000 years. So the last ice age ended about 10,000 years ago. So see, this is, we have 2,000 here and 8,000 here. So that's 10,000 total, 10,000 years ago. Because here we have year 0, not years ago. So about 10,000 years ago is considered the end of the ice age. And so the blue line here is a reconstructed temperature. So, because of course we didn't start directly measuring temperature until the 1800s. So we don't have any direct temperature measurements that are more than 150 years old. Before that, our temperatures are estimates, mostly from ice cores. So in the ice in Greenland and Antarctica and a few other places, there is a record of the atmosphere going back thousands of years. And you can analyze the gas in bubbles of trapped atmosphere and using the isotopes present, approximate the temperature. So what you see here, the light blue, that's the error margin here. So the real temperature was somewhere in the blue, and the dark blue line is the best estimate. So you can see that temperatures warmed at the end of the ice age. So this is the peak here, is 10,000 years ago. And then they remained fairly stable until about 4,000 years ago. And then they started steadily declining. And when this trend was discovered, the ice cores first started to be sampled in the 1960s and 70s. Scientists were quite alarmed by this downward trend, and I remember stories in the news in the 1970s that, are we headed for another ice age? Look at this downward trend in temperature that's been discovered, and what does it mean? And, maybe we're going to be fighting off an ice age in another 100 years. And now we have the red light here, which is directly measured temperatures. And we can see here, directly measured average worldwide temperature is in fact hotter than anything since the end of the last ice age. Now, it's not the hottest that the Earth has ever been. The Earth has been much hotter than it is today during the entire age of the dinosaurs, and in fact for several million years after the end of the age of the dinosaurs, the Earth was hotter than it is today, and it was pretty much tropical environment over the entire Earth. There was no permanent ice at the poles. So we're not the hottest we've ever been. It's the hottest since the end of the last ice age. So this certainly does look like the current warming is unusual and not just part of some normal up and down trend. So how hot is it going to get? So this is a projected increase for over the next century, so to 2099, so that's the next 80 years. And if you notice here, the Arctic and the Antarctic look like they're going to warm the most, especially the Arctic. And that's partially because the Arctic is actually ocean. There's no land up here at the Arctic. It's an ocean that has floating ice in it. And ice and snow are reflective. They reflect a lot of solar radiation back into outer space. And when that starts to melt, open water absorbs heat. We no longer have that reflective surface. So that's one of the reasons why the Arctic is slated to increase in temperature the most. And an average percent increase, so this isn't degrees of average increase, this is a percent increase. So at the extreme here, that's an increase of a few degrees, which that might not sound like much, but an average global temperature increase of only a few degrees is what happens during the ice ages. During the ice age, it only drops a few degrees. In between ice ages, the average global temperature only goes up a few degrees. So a few degrees makes a huge difference. So what about our state of Illinois? What's going to happen? So this is a projection for climate. If we can compare it today, if we move Illinois further south, what the climate is going to be like. So we have a moderate projection and a more severe projection. So worst case scenario, in 80 years, the environment and the annual climate in the Chicago area could be more like East Texas, which would mean extremely rare snowfall, temperatures during the summers topping 100 degrees for weeks at a time. It would be a significantly different climate, and many of the native animals and plants in Illinois could not survive that climate. And many native animals and plants are going to go extinct or be extirpated locally and be replaced by other ones. So what do we know about what causes the local or the global climate to change? Well, there are four main gases that are thought to be involved with the greenhouse effect. So the greenhouse effect is actually a good thing, because if we didn't have the greenhouse effect, the Earth's temperature would change drastically between daytime and nighttime, like it does on planets where they have a very thin atmosphere, like on Mars or on the Moon, which has no atmosphere at all. There's a change of about 400 degrees between day and night. So the greenhouse, it's like a blanket. It helps keep the warmth in from the sun and helps keep the surface of the Earth livable and helps protect us from extremes in temperature. And the four gases that are involved with that are water vapor, which we really can't do much about, carbon dioxide, and methane, with carbon dioxide being of more concern because it's persistent in the atmosphere. Carbon dioxide is very stable. It has a half-life in the atmosphere of thousands of years. Methane is a more severe greenhouse gas. It holds in more heat per molecule than carbon dioxide does, but it's also unstable. And in the atmosphere, it has a half-life of about 20 years, not thousands of years. So methane is unstable and tends to break down into carbon dioxide. So it's of less concern for that reason, because it's less stable and persistent in the atmosphere. Nitrous oxide is also produced by burning fossil fuels and increased in the atmosphere, although it is a naturally occurring compound and does occur naturally, just like, you know, carbon dioxide, methane are also naturally occurring and have natural sources as well, not just industrial sources. So in this complex picture here, what you should focus on is here's incoming radiation from the sun, and several things can happen to the incoming radiation. It can be absorbed by the atmosphere, by clouds, by the surface, whether it's land or water, and some of it is reflected back into space. So very light colored surfaces like snow and ice reflect it back into space, and also the tops of clouds reflect some of that solar radiation back into space, which you can tell, you know, standing outside on a cloudy day. It feels cooler than if you're standing outside on a sunny day, even if the temperature is exactly the same, because you don't have as much solar radiation directly striking you. So if it's cloudy, some of it's being absorbed by the clouds and some of it's being reflected back into space by the clouds. Radiation, heat radiation is also being emitted from the surface and heading for outer space. And again, water vapor in the atmosphere and clouds tend to hold that heat in, which is why when it's humid, it stays hotter at night in the summer. So if it's very humid, even if there's no clouds, it can stay very hot at night because that water vapor helps hold the radiation in. Clouds help hold the radiation in. So our coldest days in the winter and our coldest nights are usually cloudless ones. So when it's cloud-free at night and the humidity in the winter is very low anyway, all that radiation can go right into outer space and it causes more cooling at night. So greenhouse gases help trap some of this heat radiation and keep it from going into outer space and help it bounce back down into the atmosphere. So carbon dioxide and methane and water vapor help keep that in. And that's the greenhouse effect, is keeping that solar radiation in the form of heat now, because once it's been absorbed by surfaces and it's being radiated back out, it's heat. So some of that is a good thing. So how do we know whether there's a correlation between carbon dioxide and methane and temperature? Well, if we go back to our ice cores that we use to estimate the temperature, so that's what's down at the bottom here. And so now we have a little bit different, we have three graphs here, one right on top of the other with the same years here. And this data is from ice cores. So this is now thousands of years before the present. So on the far left now is now. And on the far right is several ice ages ago, 500,000 years ago. So 500,000 years ago over here. And you can see that in the temperature here, the ice ages. So low temperature is Ice Age, warm is Holocene, or is a warm period. This is the Holocene over here, sorry. Ice Age, warm period, Ice Age, warm period, Ice Age, warm period. And how does that correlate with the gas in the atmosphere? So when the temperature is warmer, so here's a warm peak, high methane, high carbon dioxide. So the red is carbon dioxide, the green is methane. So when the temperature's high, so is the methane and the carbon dioxide. Methane, carbon dioxide. So they seem to correlate very, very well. The amount of CO2 and methane in the atmosphere seem to correlate very well with the temperature over the last, well, in this particular graph, 800,000 or 500,000 years, but we have ice cores going back 800,000 years. So what about, how does that compare to CO2 today? So here we have global temperature is the blue and red line, and it's red when it's above this arbitrarily selected zero value here for average. And the green line is CO2 levels. And so this now, the present is on the right, and 450,000 years ago is on the left. So this graph is the opposite of what that previous one was. So now we have temperatures going up and down and up and down. So interglacial, glacial, interglacial, glacial period. So here's the last ice age that ended, started ending about 12,000 years ago and is considered to have ended completely 10,000 years ago. We see temperatures rising, and CO2 levels, though, look at the CO2 levels. So, and now even in 2019, carbon dioxide for the first time topped 400 parts per million. So it's even above the top of this graph here. So it certainly doesn't look like it's just a part of normal fluctuation. And the temperature is increasing, but hasn't quite caught up yet. So CO2 levels are the highest in the last 800,000 years. They're not the highest they've ever been. So when the Earth was much warmer than today, during the age of the dinosaurs, CO2 levels were higher than 2. Methane levels were higher than 2. So it's correlated with higher temperatures globally. So this kind of predicts that we should expect temperatures to continue to increase because CO2 is so high. It's the highest in the last 800,000 years, but not the highest it's ever been. It's been higher before. Are humans doing it? Are we the reason that CO2 seems so weirdly high right now? So here is CO2, methane, and nitrous oxide just for the last 2,000 years here. So this is the year, so year 0 AD to the year 2010. On here, oh, it's up to 2005 over here. And you can see very clearly right around 1700, things start to increase. Wonder what happened in the 1700s. So that's when the Industrial Revolution began, which meant what that means for those atmospheric gases is that in the 1700s, we started burning coal, and first coal, and also wood and oil eventually in very large amounts. And it has taken hundreds of years for it to build up in the atmosphere to the levels that it is today. And it hasn't built up as much as models predict. And that's partially because the ocean has absorbed more CO2 than was expected. Deforestation also increases warming, so it's not just the burning of fossil fuels, burning of wood that's increasing CO2. When you stop photosynthesis, that also increases CO2. So forests are huge photosynthetic factories. They remove CO2 from the atmosphere and turn it into larger molecules like cellulose, that's a major component of wood, but also sugars and proteins and lipids that are found in plants. And so that's removing CO2 from the atmosphere. So when you cut down a forest, that forest is no longer photosynthesizing and removing CO2. So, and generally, when we are cutting down forests, we are replacing it with farmland or a plantation or something. So, and those do not absorb as much CO2 from the atmosphere as a dense forest does, or even then a grassland does. So when they change tall grass prairie in Illinois into wheat farms and corn farms and soybean farms, that also absorbs less CO2 from the atmosphere than the tall grass prairie. So that's another reason why CO2 is increasing. It's not just the burning, it's also removing land from its natural photosynthetic state. So another way we know that humans are affecting global warming is when there were fewer humans, the globe cooled, and the Black Death is one of the things that contributed to that. So the Black Plague, bubonic plague, killed 50 to 60% of Europe's population in Asia. Starting in 1350, there were multiple plagues over many centuries that finally petered out in the 19th century. And they decreased the population of Europe and Asia. And the Black Death went all the way from Britain on the west, all the way to Japan, south to India. So pretty much the entire Eurasian continent was affected for centuries. The total population of those areas declined. And when that happened, there was farmland that reverted to its natural state. There were fewer fires. So this was even pre-industrial revolution. And the amount of CO2 in the atmosphere declined. And at the same time, we have human population in Europe and Asia declining. We also had human population in the Americas declining because Europeans had finally made it to North and South America, bringing diseases and weapons with them that decimated the Native American populations at the time. Millions died after Europeans arrived. So that could have contributed to this as well, although it hasn't been as thoroughly researched as the Black Death link. So decline in atmospheric CO2 led to the Little Ice Age. The Little Ice Age was a temperature anomaly that occurred from about 1400 until close to 1900, where there was a dip in global temperature because of there being fewer people. There were fewer cooking fires, there was abandoned farmland, there was less logging of forests, and that decreased global temperature. So this shows that people affect global climate, and we have been for hundreds of years. This is not just something that's happened since the Industrial Revolution. And the last question, is global warming bad? So because this is a subjective question, remember, questions that are a matter of opinion, if we're going to answer them scientifically, we have to turn them into a much more specific question, something that we can address scientifically. So instead of being vague and saying, is it bad, we can ask, how many species are expected to go extinct? Which environments are going to be most negatively affected? Which populations in the world are going to be affected? Exactly how much is the ocean expected to increase in elevation? Things like that. So we have to turn it into a more specific question. So the Arctic sea ice has been decreasing, and we don't know the extent of the Arctic ice going back very far, because this only became a thing once we had satellites circling the planet taking pictures. So we only have a very good record of the Arctic ice going back to the 1970s. Before that, it was explorers' reports and sea captains' reports, and we don't have a whole picture like we do now. But it's declining so much, these two pictures are the minimum. So in the winter, the sea ice expands, and in the summer, it shrinks. And you can see these are from September 1984, September 2012. So this is what they call the sea ice minimum. And the extent of the sea ice during the minimum has gotten smaller and smaller, so that they expect possibly by 2050 there will be no ice whatsoever at the North Pole in the summer. And this is causing a positive feedback loop. So a positive feedback loop is when something increases the effect. So the positive feedback loop here is that the snow-covered ice is highly reflective, but the dark surface of the water absorbs energy from the sun. So the more expanse of open ocean there is, the more it's going to warm. So as you have less and less ice in the summer, that actually increases the rate at which the Arctic Ocean is warming. So sea level is expected to rise in the next 100 years by about 20 feet. And that's going to affect some areas very severely. So if we look at a map here of the east coast of the United States, and how high above sea level in meters. So 1 meter is about 3 feet. So 20 feet would be about right here. So that means that all the areas that are red or brown or black here are going to be underwater by the end of this century. And so you notice that includes a large part of Louisiana and huge areas of the coast, most of southern Florida, huge areas of some of these East Coast states. So everything that's red here is going to be ocean in 80 years. And you'll notice there are some Caribbean islands here that are going to be in trouble as well when that happens. There's at least one island nation in the Pacific that has already relocated because the little bit that sea level has increased already has caused most of the island to become uninhabitable. Some species may go extinct because of this. So the sugar maple, this just shows the extent of the sugar maple tree in the United States, but it also exists in Canada up here. I don't know why they chose not to show it in this particular illustration. But sugar maples are very temperature sensitive and they cannot survive in warmer states. Well, if the climate here changes, a large section of the sugar maple ecosystem here may become unsuitable for sugar maple trees. And then they may only exist in the more northerly parts of their habitat. And there's many species that will be affected by this. Animals can move. Plants also can move, but they move by their offspring moving. So trees themselves don't move, but year after year after year, sugar maples could slowly be found only in the more northerly regions, although they can't move as fast as animals since they move generationally. Will there be any benefits to global warming? Maybe. There's going to be arable land that is currently not arable land. So arable land is land that we can farm or use for rangeland. And there are areas in Canada and Siberia today that are too cold to be arable land, but that could change. So maybe there'll be new areas, maybe the big grain growing areas of the world are going to shift north. Some dry areas are going to get more rainfall. This is already apparent in the Midwest. The Midwest rainfall has increased in the last 20 years. Some years it's actually been so wet, like 2019, that farmers in the Midwest had a difficult time planting in the spring because there was so much rain. Tropical and subtropical areas are going to expand, and so will the crops that will grow there. So crops that currently cannot be grown in the United States because they are tropical maybe could be grown in Florida and Texas 50 years from now. Let's talk about some environmental success stories, because it's not all doom and gloom. The story of the ozone hole is one of those success stories. It was noticed, thanks to new satellite data that started to become available in the 70s, that ozone in the atmosphere, which was known to protect us from ultraviolet radiation, was doing something weird over the South Pole. At certain times of the year, there was a hole in the atmospheric ozone, which is not visible to the naked eye. It was only visible to instruments that were present in satellites and on ground collecting instruments. And it was allowing an increase in ultraviolet radiation to strike the surface. And this was very alarming, because as this hole was getting larger and larger, it was eventually going to expand into areas where humans lived. And increased ultraviolet radiation, besides causing skin cancer, ultraviolet radiation affects plants in a negative way. It affects all living things. Ultraviolet radiation is the lowest level of radiation that can damage DNA. So that would be bad. And it was discovered the reason for the ozone hole was a chemical that had been used for decades. Chlorofluorocarbons were used in refrigeration, and they were incredible when they were first being used, because what preceded them was ammonia. Ammonia-based refrigeration was dangerous because if it sprung a leak, it could kill people. CFCs did not kill people if they sprung a leak, but massive quantities of CFCs were leaking into the atmosphere, and they were destroying the ozone in the atmosphere. And they're extremely persistent in the atmosphere, lasting for decades to hundreds of years in the atmosphere. So The Montreal Protocol was an international treaty. 196 nations agreed to stop the manufacture of CFCs like Freon, first by cutting it in half by 1998 and then eliminating it completely. So almost nobody is using these CFCs anymore, except for some very specific industrial purposes. And the expansion of the ozone hole has stopped. It's not expected to recover for decades, however, because of the persistence of these chemicals in the atmosphere. But the elimination of these chemicals from common use made an immediate and measurable difference. So we call that a success. So here is the ozone levels, 1955 to 2005. Ozone levels over Antarctica were dropping, and then now they've stabilized. And there's even been a few higher readings here, higher than in 20 years. So it's expected to slowly continue to improve. But it took 50 years to decline. It would probably take another 50 years to recover. But we call this a success. And it shows what happens when governments get involved and regulations force businesses to do something, because businesses would never have done this on their own without government regulation. Acid rain is another partial success story. Acid rain results from burning fossil fuels, especially coal, but also oil. So the pollution generated from burning these things, it gets into the atmosphere and it mixes with the water and creates acidic compounds. So sulfur dioxide, which is especially from the burning of coal, but is also present in oil, and nitrogen oxides, also found in coal and crude oil. And this is because of where those fossil fuels originally came from. Those fossil fuels are from plants that were compressed into a layer millions of years ago and did not completely decompose. And sulfur and nitrogen compounds that were found in the proteins in those plants are still there. So they form sulfuric acid and nitric acid when they mix with water in the atmosphere, and then they rain back down, or snow, and create an acidic environment in the soil and in water, in lakes and rivers, and also in the soil. So what's the problem with acid? Well, it prevents plants from taking up nutrients. If it's the wrong pH in the soil, the nutrients, minerals like phosphorus and calcium stay in the soil instead of being able to be absorbed by the plants. It also, if it acidifies lakes, this can kill fish. So the problem of acid rain has improved dramatically. Now, this was not a huge problem in Illinois because the wind in the United States tends to go from west to east. So this was an East Coast problem. It was less of a problem in the Midwest because we don't have as much big industry going on, and not to the west of us anyway. So, but it has dramatically improved since the Clean Air Act went into effect in the early 1970s, and other regulations that force businesses to scrub the sulfur from their emissions, and that greatly reduces the acidifying of the rain that mixes with the pollution. So regulations have had a huge effect on this. Conservation efforts are ongoing and changing. Conservation biology is now a field of study, which it wasn't until the 1980s. The Endangered Species Act in 1973 really limits habitat destruction if an endangered species is present. It eliminates the hunting of endangered species. It has now been weakened. The current administration has said they are not going to enforce the Endangered Species Act. There's an international treaty on the trade in endangered species, the Convention on International Trade in Endangered Species, abbreviated CITES. And this prevents the import of endangered species like elephant ivory, tiger skins, things like that. And this is also not being as enforced as strictly as it was. But people are much more mindful now of habitat protection, habitat restoration, where farmlands aren't being used anymore. They are being restored to their tall grass prairie condition or deciduous forest condition that was there before. Captive breeding and reintroduction is used, but it's very expensive. It's easier to restore the habitat and let the wild creatures do their thing rather than trying to breed them in captivity or clone an extinct species, although those things are also being done. Another success story is our national bird, the bald eagle, which was on its way to going extinct in the lower 48 states in the 1970s. And there are still people who argue that it wasn't DDT, although DDT seems to have been a contributing factor. DDT is a pesticide that was banned in the United States in 1973, partially because it's very persistent in the environment. It is persistent in bodies. It's fat soluble. And so eagles being at the top of the food chain and other birds of prey were accumulating large amounts of it in their bodies. And there is some good evidence that it was thinning the shells of their eggs and leading to poor reproductive success. But since the Endangered Species Act was passed, it made it illegal to hunt bald eagles, which is surprising, I know, that people used to hunt bald eagles just for fun. And that was banned. And also banning DDT, their population has made a slow and steady recovery. Even here in the Midwest, I grew up in the Midwest and I never saw a wild eagle until the 1980s. That was the first time I ever saw a wild eagle in my home state. And now they are everywhere. And I even had a bald eagle eat one of my chickens a few years ago. And they were welcome to it. So things have changed significantly, and it just shows you how a well-crafted law, the Endangered Species Act, and banning dangerous substances like DDT can make an enormous difference. Not all species recover easily. Whales have a very slow reproductive rate, and many whales are not recovering well, even though most whale species are no longer being hunted. Some whales, like minke whales, are still being hunted by Japan and other countries. And even with the low amount of catch that's continuing to go on, because their population is already low, and they have a very slow reproductive rate, with females not being reproductive until they're 7 or 8 years old and only having one baby every 2 years or so. That means that even with a low number of annual kills, it may make it impossible for that species to recover and cause them to go extinct. Captive breeding can be successful. The California condor experiment is still ongoing. So the California condor is not the heaviest North American bird, but it has the largest wingspan of 3 meters or almost 10 feet wingspan. They were functionally extinct in the wild in 1987, and all 27 remaining wild California condors were brought into captivity and into a very intense breeding program, both at the San Diego Zoo and also LA. And today, they've gone from 27 individuals in 1987 to 488 individuals. And many of those are living in the wild. There are now wild California condors in California, in Mexico, and in Arizona. So it's a moderate success, and many of the released animals have been hit by cars and poisoned by ranchers accidentally. But they're educating the ranchers and farmers in the areas about how not to accidentally kill the condors, and that's made a huge difference. This photograph shows them rearing the baby condors with puppets. So this, what looks like an adult condor, is actually a human hand and a puppet. They didn't want the condors, because condors are intelligent and they will become acclimated to humans, and they didn't want them to be acclimated to humans. So they tried to never let the baby condors see a human. So they only saw these puppets, these condor puppets. And it actually worked really well. And why not just let the parents raise them? Well, the condor parents did raise some of the babies, but what they would do is, as they were laying their eggs, they would take some of the eggs and put them in an incubator and raise them by hand, and then leave some of the eggs behind, because then they would lay more eggs. So they were able to increase the reproductivity of these slow reproducing birds by raising some of the babies by hand and letting the parents raise some of the babies. So, and they're continuing to release them into the wild, and every single one of them is tagged, and they are protected, and they track them and follow them and try to find out what happens to them. And there have been quite a few wild raised California condors now that have survived in the wild and reproduced in the wild. So moderately successful, hopefully continuing to be successful. The elephant ivory ban has also been somewhat successful. Elephants were headed for extinction 50 years ago because of elephant ivory, which was used for everything from piano keys to buttons to religious statues, jewelry, and with the ban on trade in elephant ivory, the elephant population is still declining because there continues to be an illegal trade in elephant ivory, but the decline has slowed. Elephant populations are still declining, but not as rapidly. They're still heading for extinction, but at least it's slowed now. Habitat loss is also a huge factor. Elephants also really like the crops that we grow, so there's a problem with farmers killing elephants that get into their crops. It's really hard to build a fence that keeps elephants out. So consequence of that, elephants regularly invade farms, and they can totally destroy a whole year's crop in one night. So that's a problem too that needs to be addressed. Wetlands are recently recognized as a valuable resource. Until the 1980s, wetlands were thought of as useless swamps that should be drained, and they were drained all over the place. As you can see in this map of the United States, there are quite a few wetlands in here, some of which just have small remnants, like the wetlands on the south end of the San Francisco Bay, Everglades. There were huge wetlands on the East Coast here, south of Washington, D.C., that there are just little remnants of. The Grand Kankakee Marsh has almost completely been drained. And if you remember, the things that contribute to biodiversity are temperature and water. So places where there's a lot of water, we tend to have more biodiversity, and that was not recognized as being anything of value until recently. So the Everglades, Florida is very flat, and it has a drainage basin. So here we have this large lake here. That's there, it just went right out of my head which lake that is. The Okefenokee Swamp? No. Oh, I can't remember it. This is the Kissimmee River, though, and this lake is the largest lake in Florida. The name's going to come to me. And the water used to flow south, from north to south, into the Everglades. The Everglades is down here. And it was decided that all this wetland was useless, and so the Army Corps of Engineers assisted with creating canals to drain water east and west to the ocean and bypass this southern region in Florida. And they dried up huge areas of marsh and swamp. And there are housing tracts there that couldn't have been there 100 years ago without this drainage. Well, this has created a lot of sinkage, and now it's been recognized that the Everglades helps protect southern Florida from hurricanes, and so they're now trying to restore some of the natural historic water flow. They can't restore it back to its original levels, however, because of all of the people who live here now. It would destroy towns if they did that, but they're trying to partially restore it, and they're eliminating some of the canals that were built to drain the Everglades and allowing the natural slow movement of the water to go back to the way it was, partially back to the way it was. Closer to home, the Grand Kankakee Marsh extended over most of northern Indiana and part of northeastern Illinois. So the dark line here is the boundary of the watershed for the Kankakee River. Here's the Kankakee River going through here, which the river is still there. And it used to, however, meander all over the place. And the Kankakee Marsh was a huge wetland that was created by this meandering Kankakee River. And it was a huge resource. There was millions of waterfowl that lived there that were a source of food for people in the area. Lots of wildlife there. And it was drained for farmland. And it was about a 50-year project to drain it. But a canal was created. The Kankakee River was straightened out into essentially a canal, which drained a lot of the land. But all of that flat land, as you drive through northwestern Indiana, you hit all of this super flat area. That's the old marsh. So we talked about how a biodiverse environment benefits people through medicine and gathering wild products and medicines. Biodiversity increases the closer you get to the equator and with increasing water availability. Human activity has been causing extinctions for thousands of years. It's not a new thing, although the rate of extinction has accelerated since the Industrial Revolution, since our industrial methods of farming and fishing and logging, we have been able to destroy the environment at a more rapid rate. Global warming is definitely occurring, and the evidence points to human activity as being the cause of the current warming trend that we are in. And it's not too late to slow it down or reverse it. There have been some conservation success stories. We talked about the reduction in acid rain, the restoration of certain species that were on the verge of extinction, the reversal of the trend of the ever-enlarging ozone hole over Antarctica. So we can make a difference, and a measurable difference. Whole habitats are necessary for species to survive. Species that rely on old-growth forest or wetlands, the habitat has to be restored in order to save that particular species. And people are trying to do these things. We now recognize the benefit of biodiversity as we have not in the past. Well, that's it for conservation and biodiversity.